Welcome everyone, and thank you for joining me today. I'm excited to introduce our topic, heat pump hot water system design. This presentation will explore the key aspects of designing efficient and effective hot water systems using heat pumps. We'll cover how to properly size these systems to maximize energy savings and ensure user comfort. Let's get started. When a system is correctly sized, it can effectively meet the hot water demand without using more energy than necessary or causing undue wear and tear on the equipment. This balance is crucial because it ensures efficiency and longevity. If the system is undersized, however, it simply can't keep up with the hot water demand. This can lead to discomfort for users and operational problems, like running out of hot water when it's needed most. On the other hand, an oversized system might seem like a safe bet, but it actually causes energy waste and increases the initial investment costs. So, the key takeaway here is that proper sizing is essential, not only for comfort and reliability, but also for optimizing energy use and controlling costs. This concept ties into the overall goal of designing efficient, sustainable systems that serve the needs of users without unnecessary expense or resource use. In this video, we will break down the key parameters and calculations involved in sizing a heat pump system. We'll explain the main components involved and show you how to select the right capacity heat pump and storage tank for your needs. Understanding these elements is crucial because it helps engineers, designers, and facility managers optimize their hot water systems. By doing so, they can save energy, reduce operational costs, and ensure a reliable supply of hot water. This knowledge is fundamental to making informed decisions that improve system efficiency and performance, which ties directly into our overall goal of creating smarter, more sustainable heating solutions. Please note, every day, people use hot water for showers, cleaning, cooking, and more. But have you ever wondered how engineers make sure there's enough hot water for everyone, especially during busy hours? Let's break it down. In this system, the daily hot water demand is 25 cubic meters. That's 25,000 liters used in just one day. Now, water use isn't evenly spread across the day. Most people tend to shower or do laundry in the morning or evening. Understanding this pattern helps engineers plan and design systems that can meet these peak demands efficiently. So, by analyzing when and how hot water is used most, we can ensure everyone has enough hot water when they need it most, which ties back to the overall goal of creating reliable and efficient hot water systems. So, engineers plan for a peak flow, the time when usage is at its highest. Here, the system needs to supply 3.8 cubic meters per hour over a 4-hour window. That's quite a lot, and it's important to understand that this figure is based on the hottest part of the day, when demand is at its peak. To put it into perspective, in those busy 4 hours, the total hot water demand amounts to about 15 cubic meters. This calculation considers that roughly 60% of the total daily hot water demand occurs during this peak period. We arrive at this figure by taking the total daily hot water demand, which is 25,000 liters, multiplying that by 0.6 to focus on the peak period, and then dividing by 4 hours. This helps us ensure that our system can handle the maximum expected load, keeping everything running smoothly even during the busiest times. Understanding this peak flow is crucial for designing an efficient and reliable system that meets demand without over or undersizing. Now let's talk about temperature. The incoming cold water enters the system at about 25 degrees Celsius. To make it comfortable for use, we need to raise that temperature up to 60 degrees Celsius. That's a significant increase of 35 degrees. This means the system must be capable of heating all that water quickly and efficiently. And this is especially critical during peak times when demand is at its highest. So the key point here is that managing this temperature rise efficiently is essential for providing consistent, reliable hot water while also optimizing energy use. This ties into our overall goal of creating an effective and sustainable water heating system. To do this, the system needs the right size of heaters, storage tanks, and pumps. These components have to work together to deliver enough hot water, exactly at the right temperature and at the right time. If any of these parts are too small, people might run out of hot water when they need it most. On the other hand, if they're too big, it leads to unnecessary energy waste. So getting these sizes just right is key to ensuring efficiency and comfort. This idea ties back to our overall goal of optimizing the system to be both effective and energy efficient. When designing hot water systems, it's essential to consider the daily demand, which in this case is about 25 cubic meters per day. This helps us understand how much hot water will be needed on an average day. We also need to think about peak flow, which here reaches 3.8 cubic meters per hour for a period of 4 hours. This means during certain times, the system must handle significantly higher volumes of water, so we need to ensure it can meet that demand smoothly. Another key point is the temperature rise. We're looking at an increase from 25 degrees C to 60 degrees C, which is a 35 degrees C rise. This temperature change is crucial because it impacts the size and capacity of the heating equipment we select, as well as energy efficiency. All these factors, demand, peak flow, and temperature rise, are interconnected. Balancing them effectively allows us to create systems that are not only comfortable and reliable, but also efficient and cost-effective. Ultimately, designing hot water systems is about turning everyday water use into smart engineering solutions, making sure comfort and efficiency go hand in hand with proper timing and capacity. To design a hot water system, engineers first need to determine how much energy is required to heat the water. This is what we call the thermal load. Essentially, it's about understanding the amount of energy needed to bring the water to the desired temperature. Now, to calculate this, we use a specific formula. Q equals rho times Cp times delta T times F. Let's break that down. Q represents the thermal energy or heat in kilojoules. Rho, is the density of water, which is about 1,000 kilograms per cubic meter. That's a key value because it tells us how much mass of water we have per unit volume. Next, Cp is the specific heat capacity of water, which is 4.18 kilojoules per kilogram per degree Celsius. This value indicates how much energy is needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. Then delta T, or deltat, is the temperature rise. In our case, we're heating water from 25 degrees Celsius up to 60 degrees Celsius, so that's a 35-degree increase. Finally, viz the flow rate in kilograms per second. This tells us how much water is moving through the system per second, which impacts how much energy we need overall. By understanding these variables and how they interact, we can accurately determine the energy required for the hot water system, ensuring it's designed efficiently and effectively to meet the demand. All right, let's take a look at the flow rate here. The slide states that the flow rate is 3.8 cubic meters per hour. Now, to understand the thermal load, we need this in terms of kilograms per second. So, what we do is multiply the volume flow rate by the density of water, which is 1,000 kilograms per cubic meter. But since we're interested in per second, we then divide by the number of seconds in an hour, which is 3,600. Doing that calculation gives us approximately 1.055 kilograms per second. Next, we use this flow rate to find the power needed to heat the water. The formula shown is Q equals 1,000 times 4.18 times 35 times 1.055. Here, 4.18 is the specific heat capacity of water in joules per gram per degree Celsius, and 35 is the temperature difference in Celsius. Multiplying all these together gives us roughly 154,565 watts, which we round to about 155 kilowatts. So what does this tell us? Essentially, this is the thermal load, the power required to heat the water during peak usage times. It's a key point because understanding this helps us size the heating system correctly to ensure efficient and reliable operation during the busiest periods. This calculation ties directly into the overall theme of designing effective thermal management systems. When it comes to heating water efficiently, selecting the right heat pump is absolutely essential. But you might be wondering, how do engineers determine what size or type of heat pump to use? Well, it all starts with understanding the thermal load, which in this case is 155 kilowatts. This is the amount of heat energy needed to meet the demand for hot water. Once we know the thermal load, our goal is to find a heat pump that can deliver this amount of heat efficiently and reliably. It's not just about matching the capacity, it's also about ensuring the system operates at optimal efficiency, which helps save energy and reduces costs. This decision-making process is a key part of designing sustainable and effective hot water systems, connecting directly to the overall goal of maximizing energy efficiency in building management. So, selecting the right size isn't just a technical detail. It's a crucial step toward achieving system performance and sustainability. So, what exactly is COP? Well, a heat pump doesn't actually create heat from nothing. Instead, it moves heat from one place to another, which is a much more efficient way of heating. The efficiency of a heat pump is measured by something called the coefficient of performance, or COP. Think of COP as a ratio. It tells us how much heat the pump produces compared to how much electrical energy it uses. For example, a COP of 3.5 means that for every 1 unit of electricity the pump consumes, it outputs 3.5 units of heat. This is a really important point because it shows that heat pumps can be much more efficient than traditional electric heaters, which often convert electricity directly into heat at a 1:1 ratio. So, a higher COP means you're getting more heat for less electricity, which is better for both your energy bills and the environment. Connecting this to our overall theme, understanding COP helps us see why heat pumps are such an effective and sustainable choice for heating solutions today. To meet our 155 kW thermal demand, we need to consider the efficiency of our heat pump, which is measured by its COP, or coefficient of performance. In this case, the COP is 3.5, meaning that for every unit of electrical energy we put in, we get 3.5 units of heat energy out. So, instead of using 155 kW of electrical power directly, we can calculate the actual power needed by dividing the thermal load by the COP. That gives us approximately 44 kW of electrical power. This highlights how an efficient heat pump can significantly reduce our electrical energy requirements while still delivering the necessary thermal output. It's a key point because it shows how leveraging high COP devices can optimize energy use and improve overall system efficiency, which aligns perfectly with our goal of sustainable and cost-effective energy solutions. So one option we're looking at is installing a single large heat pump. This particular option has a capacity ranging from 150 to 160 kilowatts, which makes it quite powerful. It's an air-to-water type, meaning it extracts heat from the outside air and transfers it to water for heating purposes. The advantage here is simplicity. You only need one unit to manage. It's straightforward to install and operate, which can make maintenance easier as well. This option fits well if you're aiming for a streamlined system with fewer components, all working together to deliver reliable heating. It really ties into our overall theme of balancing efficiency with simplicity in system design. The second option we're looking at involves using 2 modular units, each with a capacity of 80 kW. What's great about this setup is the flexibility it offers us. We can operate one unit while keeping the other on standby, ready to step in if needed. Alternatively, we can run both units at partial loads, which helps us increase their lifespan and improve overall efficiency. This approach really aligns with our goal of creating a reliable, adaptable system that can be tailored to different operational demands, ensuring we maintain optimal performance while managing maintenance and energy use effectively. Let's take a closer look at this side-by-side comparison chart. On the left, we have the one large unit, and on the right, the 2 modular units. Starting with simplicity, the single large unit is quite straightforward. It's simple to install and operate. In contrast, the modular setup is slightly more complex because it involves managing multiple components, but it offers more flexibility. When it comes to redundancy, the one large unit doesn't have any backup systems, so if it fails, the system goes down. On the other hand, the modular units have standby options available, which can keep operations running smoothly even if one module encounters an issue. Regarding maintenance, a single large unit typically requires full downtime during servicing, which can be disruptive. Meanwhile, with modular units, one module can be maintained or repaired while the other continues to operate, minimizing downtime. Scalability is another key point. The fixed size of a large unit makes expanding capacity more complicated and costly. Conversely, modular units are easily scalable. Adding more modules allows you to expand capacity smoothly and efficiently. Finally, looking at initial costs, the large unit is often cheaper upfront, making it attractive for smaller budgets. However, the modular approach might have slightly higher initial costs, but it offers long-term benefits like flexibility and scalability that can justify the investment. Overall, this comparison highlights how choosing between these options depends on your specific needs, whether you prioritize simplicity and initial cost or flexibility and redundancy. Now, let's look at the heat pump selection summary. First, it's important to understand what COP means. It tells us how efficient a heat pump is. A higher COP indicates better efficiency. For example, if we have a 155 kW load, that typically requires about 44 kW of electric input when the COP is around 3.5. So, the system's efficiency really impacts our energy consumption and operating costs. When choosing a heat pump, we have a couple of options. One is to go with a single large unit, somewhere between 150 and 160 kW. The other is to opt for two smaller modular units, around 80 kW each, which can offer more flexibility in how we operate and maintain the system. Ultimately, smart heat pump selection is about balancing efficiency, reliability, and long-term costs. By making the right choice, we ensure that hot water is always available when we need it, supporting both operational needs and energy savings. This decision ties back to our overall goal of creating efficient, reliable, and cost-effective hot water systems. When it comes to hot water systems, many people focus on the heater itself, but the storage tank is just as important. It plays a crucial role in making sure we have a steady supply of hot water and that everything runs smoothly. Think of the tank as the buffer that keeps things stable. Water demand in buildings isn't always steady. It tends to come in bursts. For example, in the mornings, everyone's rushing to shower, brushing their teeth, and getting ready. During that 1 hour, the system faces a heavy drawdown, meaning a lot of hot water is used all at once. This is where a well-designed storage tank makes a difference. It needs to be capable of handling those spikes efficiently, providing hot water when demand suddenly increases. So, understanding the design of these tanks helps us ensure reliable hot water supply, even during those peak times. It ties into the overall goal of creating efficient, resilient hot water systems for any building. So, why do we use a storage tank in this type of system? Well, think of it as a thermal buffer. It holds preheated water, making it readily available for use when needed. This way, the heat pump doesn't have to scramble to meet sudden demands. It's like having a reserve of hot water ready to go, ensuring smooth and efficient operation. Now, regarding the recommended tank size, we're talking about 4,000 liters. That's roughly 4 cubic meters of water. This size is ideal because it can handle a full hour of peak demand comfortably. While the system is working to catch up and reheat water gradually, this tank size ensures you won't run out of hot water during busy periods. Overall, using a properly sized storage tank helps optimize the performance of the heat pump system, maintaining efficiency and reliability. It's a key component in making sure your system runs smoothly and meets your hot water needs effectively. Let's talk about the material and pressure rating of this system. The tank itself is made from stainless steel 316, which is known for its excellent corrosion resistance. That means it's durable and safe for potable water, ensuring the quality of the water stays high over time. It's built to last, even in challenging environments. Now, in terms of pressure, the tank is rated to handle up to 6 bar. This is more than sufficient for most building systems, so you can be confident it will operate safely under typical conditions. During normal use, water flows smoothly from the tank to your taps, providing reliable supply. Meanwhile, the heat pump works quietly in the background, reheating the water as needed. This setup maintains a consistent temperature without putting excessive stress on the system, which helps prolong its lifespan and ensures efficiency. Let's talk about the benefits of having a buffer tank in your system. First, it absorbs sudden demand spikes. So, if there's a quick increase in hot water usage, the buffer tank helps handle that smoothly without stressing the heat pump. Next, it reduces short cycling of the heat pump. This means the system doesn't turn on and off rapidly, which is not only better for the equipment's longevity, but also saves energy. It also improves overall system efficiency because the heat pump can operate more steadily without frequent cycling. Plus, the buffer tank provides a thermal reserve, so if there's a delay in power supply or a brief outage, you still have hot water available. This setup really helps avoid the frequent on-off cycles in the heat pump, which extends its life and conserves energy. And it adds resilience. If the power drops temporarily, you still have hot water ready to go. It's a smart way to make your system more reliable and efficient. When we talk about large hot water systems, especially in places like hotels, hospitals, or multi-floor buildings, it's crucial that hot water gets to every tap quickly and reliably. No one wants to wait for hot water, especially in busy environments. That's where the recirculation pump comes into play. So, what exactly is a recirculation pump? Well, it's a device that keeps hot water moving through the pipes even when the taps are turned off. This constant circulation means that when you do turn on a tap, hot water is available almost instantly. No long waits, and importantly, it helps reduce water waste because we're not letting water run down the drain while waiting for it to get hot. This is a key part of making large water systems more efficient and user-friendly. In essence, the recirculation pump ensures that hot water is always on demand, supporting both comfort and sustainability in our buildings. In a typical building system, hot water leaves the storage tank and then travels through the building's pipework. From there, it circulates back via a recirculation loop. This setup ensures that hot water is always readily available right at the point of use, reducing wait times and improving efficiency. The flow rate in this system is about 4 cubic meters per hour. To put that into perspective, that's roughly 4,000 liters of water moving through the system each hour. This flow rate is carefully calibrated to match the pipe volume and account for heat loss along the way. By doing so, the system keeps the water moving smoothly without overheating or wasting energy. This balance is crucial for maintaining system efficiency and ensuring comfort in the building. Connecting this to our overall theme, it highlights how well-designed recirculation loops optimize energy use and provide instant hot water, which is vital for sustainable and comfortable building operation. So let's start with the head, which is measured in meters. The head refers to the pressure that the pump needs to overcome in order to move water through the entire system. When we say a pump has a XXX meter head, it means it can push water up through tall buildings, long pipe runs, and various fittings, all while maintaining a steady flow. This concept is crucial because it tells us how powerful the pump needs to be to handle the specific height and length of the piping system we're working with. Essentially, the higher the head required, the more pressure the pump must generate to keep everything flowing smoothly. Now, moving on to power, which is measured in horsepower, or HP. Think of horsepower as a way to gauge how much work the pump can do. It's roughly equivalent to kilowatts, which is a more common unit in many regions. The key point here is that pumps are designed to use enough horsepower to circulate water efficiently without wasting energy. Since recirculation systems often run continuously or on timers, choosing the right horsepower ensures that the pump operates effectively without drawing excessive power. In summary, understanding both the head and the power helps us select the right pump for the job, ensuring reliable performance and energy efficiency, which ties back to our overall goal of designing effective and sustainable water systems. In modern systems, the pump isn't just running constantly. Instead, it can be controlled by a timer, a thermostat, or even occupancy sensors. This means it only operates when it's actually needed, which helps to save a significant amount of energy. A recirculation pump might be small in size, but don't let that fool you. It's a key player in making your hot water system quick, efficient, and easy to use. By intelligently managing when the pump runs, we not only improve energy efficiency, but also enhance your overall experience with hot water. It ties into the broader goal of creating smarter, more sustainable systems that work better for both the environment and your daily life. Today, we're wrapping up with the key points on hot water system design, focusing on summary and best practices. Designing an efficient hot water system is more than just picking the right components. It's about ensuring that everything works together seamlessly to meet real-world demand. You want a system that can handle the actual usage patterns without waste or shortage. At the same time, saving energy is crucial, not just for cost reasons, but for sustainability too. And of course, durability matters. Your system should last for years with minimal issues. By keeping these principles in mind, you can create a hot water system that's reliable, efficient, and cost-effective. This ties back to our overall goal, designing systems that are smart, sustainable, and tailored to specific needs. Thank you so much for your time and attention throughout this presentation. I really appreciate you being here and engaging with the content. If you found this helpful, I would love for you to subscribe to my channel. That way, you won't miss out on future videos and updates. Your support means a lot and helps me continue creating valuable content. Once again, thank you, and I look forward to seeing you in the next one.